What I'm afraid of now is I'm giving you the impression that complex numbers have value only if you're doing conformal mappings. You see, complex numbers give you a degree of consciousness, so to speak, above the real numbers. Let me give you an example of another problem that used to hang me up when I was an undergraduate student learning calculus. I'm going to apply complex valued results to real series now. Remember the geometric series? 1 over 1 minus u is 1 plus u squared, etc. In other words, summation n goes from 0 to infinity u to the n. And that converges for the absolute value of u less than 1. Let's suppose now I replace u by minus x squared. If I do that, I get 1 over 1 plus x squared is 1 minus x squared plus x to the fourth minus x to the sixth, etc. In other words, summation n goes from 0 to infinity. I want my signs to alternate with the first one being positive, so I put in minus 1 to the n, x to the 2n, and that converges for the absolute value of x less than 1. Now let me just focus my attention on a question for you here, and I'll come back to this. I want to come back here in a second. But the idea is, what goes wrong when x equals plus or minus 1? You see, let me show you what I mean by that. When I saw this series for the first time, and somebody says, look at, you got to be careful when the absolute value of u is equal to 1. In other words, be careful when u equals 1 or minus 1. Well, minus 1 didn't bother me that much, but 1 I could see right away what went wrong. Namely, when u is 1 here, 1 over 1 minus u is 1 over 0, which is undefined, and I expect trouble over here. On the other hand, when the absolute value of x equals 1 here, that means that x squared is 1. I mean, whether x is 1 or minus 1, x squared is 1. Look at, nothing goes wrong over here. 1 over 1 plus x squared is perfectly well defined at x equals 1. I would expect, because my upbringing was such that I always thought that the bad points occurred where the denominator blew up. But see, this denominator never blows up, because 1 plus x squared is always at least as big as 1. Provided what, of course? That x is real, because the square of a real number can't be negative. That's the hint, by the way. The square of a complex number could certainly be negative. And here's what I'm saying. If I now take this real valued series and convert it to a complex valued series by replacing x by z, all right, using the same ratio test, etc., that we did before, I can prove that this infinite series, this power series, converges to 1 over 1 plus z squared, provided the absolute value of z is less than 1. Now, by the way, what does it mean to say that the absolute value of z is less than 1? It means that z is less than 1 unit from the origin. It means that in the Argand diagram, z is inside the circle, centered at the origin, with radius equal to 1. But here's the key point. When I look at this, I'm not at all upset that something can go wrong on this circle. Namely, 1 over 1 plus z squared factors into 1 over z plus I times z minus I, and certainly I am leery of letting z either equal minus I or I, because it's going to make my denominator vanish, and even in the complex numbers, as you recall from our first lecture on complex numbers, you cannot divide by 0. In other words, at a glance, I recognize that z equals plus or minus I is trouble. In other words, going to the Argand diagram in this picture, I know I'm in trouble at these 2 points on the circle absolute value of z equals 1. Remember, this is a circle. It's the locus of all points in the Argand diagram, 1 unit from the origin. Now, remember what we said about the circle of convergence, that set S, where the power series converges, there is a circle such that inside the circle, the thing always converges. Outside, it always diverges. Consequently, the fact that I have 2 bad spots over here tells me that I cannot go beyond this circle in talking about what happened with the power series expansion for 1 over 1 plus z squared. Notice that all I require is that something go wrong on the circle. There are infinitely many points on this circle, and the likelihood that the point at which things went bad happened to be at the point where the circle crossed the x-axis is particularly small. In other words, speaking from another point of view, if I have the good fortune to be able to be standing in the complex number world looking down at this circle, I see what went wrong. If my perspective is limited to the x-axis, I can't see anything that went wrong, and I can't understand why I can't expand this circle further. In other words, the bad spots are on the magnitude of z equals 1, but not at the point z equals 1 or z equals minus 1. These were good points. See, these were good points. These were the bad ones. But all you needed was one bad apple to spoil the whole circle, so to speak. And at any rate, I think that's enough to make my point. The point being that by studying complex series, we do two things. One is we get a larger hold on the set of analytic functions which help us in things like conformal mappings and other things which we haven't gone into. And secondly, it gives us a new perspective at series involving real power series, because we now have an extra dimension from which to view the power series. At any rate, we'll talk about other aspects of complex variables, namely